Ian, and welcome to session number 14 of our BA2 lecture recording. Today we're going to be looking at long-term decision making. This chapter involves a recap on compounding and discounting, which you would have covered at BA1, and the application of those principles like the time value of money, and we use them to calculate net present values, which we'll eventually use also in internal rate of return calculations. We'll look at accounting rate of return and also payback period. So those four are going to be decision mechanisms if you're going to make long-term investment decisions. You have those four to choose from. So that's what we're going to be looking at in this chapter. Like I said, the first part of it is a recap on compounding and discounting and the time value of money. So make sure you understand the concept behind those basics, so that when you get to calculations of NPV, for example, you've got a firm understanding of the whole concept, and it will be easy for you to apply it and understand and to make decisions using those four techniques that we're going to look at. So our starting point is the time value of money. So you've heard before people saying a bird in hand is worth two in the bush. So that same applies to money. We're going to say an amount received today is worth more than the same sum received a year later. Okay, so we say money received today is worth more than money received in the future. And that is true for several reasons. The first reason that we always quote for that is the ability to earn interest. The ability to earn interest. If you have money today, if you have 1,000 rand today, you can actually take that money, deposit it somewhere and earn interest on that money. Whereas if you're going to receive it next year and it's still the same money, that means you have missed out on a chance to actually earn interest. Okay, so that's the first reason why having money today is worth more than the same amount in the future. The next thing we'll look at is the effects of inflation. Okay, remember, inflation rarely ever goes down. You know, you never hear of prices going down on a large scale. Usually it's prices going up, up, up. So if you've got 1,000 rand today, what you can buy with it today is probably less than what you can buy with it in a year's time. So that's inflation. So inflation erodes value. Okay, it washes away value, and after a while, the same amount of money can only buy you less stuff. All right, so that's the effect of inflation. Then lastly, what we look at is risk. Risk. When we talk about risk, is a lot can happen from today and the time you're supposed to receive that amount of money. Okay, so imagine that you have given somebody money, and you're asking them, when are you going to pay me back? One person says, hey, I'll give you this money back tomorrow. The other person says, I'll give you this money back in 3 months. And it's the same amount. So now, disregarding the idea of earning interest, it's still highly likely that you choose the person who's going to give you back the money tomorrow. That is because it's less risky. You see, the longer the time from now until you get that money, the more stuff that can happen in between that may even prevent you from what? Getting that money back. The extreme case is where a person, therefore, dies and before they pay you the money. So if they're going to pay you tomorrow, the chances of a person dying from today and tomorrow, between that time, are less than the chances of a person dying within a year. Okay, so the length of time increases the risk involved. So those are the three factors. Number one, we said the ability to earn interest. Number two, we said impact of inflation, where inflation generally erodes away value. And lastly, it's the element of risk that is involved. So those are the three reasons why money today is worth more than money tomorrow. Now, in real life, when we're doing investment appraisal, calculations, etc., or investment decisions, we have to take account that idea that money today is worth more than money tomorrow. Especially since when we're doing appraisals, we're dealing with forecasts of money or cash flows that are in the future and not today. So we have to bring them to today's terms to see how much is it worth now, how much we need to invest today to earn so much in the future. Okay, so the time value of money is paramount there. It's very important. So we're going to be utilizing it whenever we do our net present value calculations, our internal rate of return calculations. And you'll keep seeing this concept of time value of money throughout the whole syllabus. Up until you finish, you're done with your CIMA studies at strategic level. You'll still see it at F3, you'll still see it at P3. So this is a very integral part of your studies. You must understand it. Make sure you grasp everything, and please take time to understand the whole line as it starts from compounding, discounting, and then how it's used in decision making. All right. So we're going to start by looking at simple interest. Now, interest under simple interest is paid or received on the principal only. So for every year that you have invested a certain amount of money, you get paid interest only on the initial amount that you invested. So the interest is calculated as principal times the rate as a decimal times n, which is the number of periods which you have invested the amount for. Okay? And then the future value is therefore simply the sum of the initial principal plus the interest. Okay? Now, that is very simple. P in that formula represents the amount invested. R is the interest rate per annum as a decimal. And N is the number of years or the number of periods which you have invested the amount for. So this is very simple. We're just going to look at an example. So it says £1,000 is invested for 5 years. The sum earns 10% simple interest each year. How much will accumulate by the end of the 5th year? Okay, so we jump straight to our formula. The future value at the end of year 5 is P plus P times R times N. P is £1,000 plus, in brackets, that £1,000 times 0.1, that's for 10%, times 5, which is the 5 years. And you get a total of 1,500. So what this means is the interest we have earned is £500 from the initial principal of £1,000. The total now, 1,500. Now let us contrast this simple interest with the more common but a bit more complicated compound interest. Now with compound interest, the interest is paid or received on the principal plus all the accrued interest. Okay? It's interest based on the principal plus any accumulated interest. Okay? So S equals X multiplied by 1 plus R to the power of N, where S is the value after N years, X is the amount invested or the principal, R is the annual rate of interest as a decimal, and N is the number of years or the number of periods. So again, this formula is very easy to grasp, and we'll look at an example to see how it operates. So we're given the same scenario, £1,000 being invested over 5 years for at 10% per annum, except in this case, it's now compound interest, no longer simple interest. So the question is asking us, find the value of the account to the nearest pound after 5 years and calculate the interest earned. So value after 5 years is simply, we've input in our formula, S equals X multiplied by 1 plus R to the power of N, which is equals to our X is £1,000, our R is 0.1, our N is 5. And so if you do it correctly, your calculator should be showing you £1,611. Okay? So after 5 years, 10% per annum compound interest with an initial investment of £1,000, your value now or your account should now have £1,611. So the interest is simply the total value of the account after 5 years less the initial amount of 1,000. So the interest is £611. Now if you can contrast that with the interest earned under simple interest, it was only 500. Okay, so as the years go by, the difference between the two diverges, it becomes greater. And as the amount of interest earned increases, the amount of interest to be paid annually increases as well. That's why people who invest large amounts of money and under compound interest will earn much, much more money over the long term than people who just invest annually and then they recoup their interest. Okay. Now, this calculation could have been done in another way. So we'll just look at the other way so that you understand where the formula came from. What we're actually saying is that 1,000 that you invested, in the first year it earned 10%, and so the value at the end of year 1 was 1,100. Okay? And then in the second year, you earned another 10% on the 1,100. Okay? So it's 1.1 times that 1,100, and you'd get the final value of 1,210. In the third year, you're earning 10% on the 1,210 to give you 1,331. And you keep doing that until the end of year 5, which will give you 1,611. Okay, so that one-line formula is the equivalent of doing 5 separate calculations. Okay, don't you just love maths? Makes work a whole lot easier. So now you may be wondering, what happens if the interest is paid more than once in a year? Think of it, when you went to the bank, the last time you went to the bank, if ever, to get a loan, they quoted you a certain rate per annum, but that interest wasn't being paid per annum, was it? You were paying the interest on a monthly basis, even though the rate that you were quoted was an annual rate. Okay, so how much were you paying per annum, therefore? Okay, so if you've got interest which is paid more than once per annum, you use the same formula, right? S equals x multiplied by 1 plus r to the power of n. But make sure that the interest rate used matches the period of payment. So if you're paying annually, that means n equals 12. So that means you must also divide your annual rate of interest that you are given. Let's say you're given your annual rate of interest is 12%. Then you must also adjust it to reflect that you're paying 12 times. So you divide it by 12. So your monthly rate of interest will actually be 1%. Okay, it will actually be 1%. So we're going to look at an illustration just to see how that would turn out. So our illustration says £500 is borrowed and it's paying interest at a rate of 1.2% per month. So how much will be owed after 1 year? How much will be owed after 1 year? So our formula is still the same. Okay. So after 1 year, the initial amount we invested was 500. So 1 plus, what is R? Remember I said R has to be a decimal. So if it's 1.2% as a decimal, that's 0.012. 0.012. Okay, to the power of 12. To the power of 12. And you'll find to the nearest, it's going to be 577 pounds. 577 pounds. Okay, so that's how you do it. Please remember, your R should always be a decimal. Okay, your R should always be a decimal. This is very simple maths. There's nothing complicated so far, and I guarantee you most of it is going to make a lot of sense. It's going to be just very intuitive. You shouldn't have problems with these calculations, at least not yet. So now let's look at equivalent annual interest rates. So as has been mentioned before, a lot of times compound interest is actually paid more than once a year. So the effect that it has is that you end up actually paying more, usually, than the quoted annual rate. So you have to calculate an equivalent annual interest rate. An equivalent annual interest rate to see if I'm paying 1% per month compounded, what will be the result after a year? Will it still be 12%? Well, let's see. So the formula for calculating an annual percentage rate is simply 1 plus r to the power of n minus 1. Okay? 1 plus r to the power of n minus 1. Okay. So that n is representing the number of periods or the number of payment periods in the year. So if you're paying monthly, your n is equal to 12. And that means R as well must reflect the monthly rate and not the annual rate, because the annual rate is what we're actually looking for. Okay, so R equals the period interest rate, whether you're paying quarterly, monthly, biannually, it doesn't matter. The rate that you're using for that period as a decimal again, and N is the number of compounding periods in a year. Okay, so that's the formula you would use. So again, we're going to look at an illustration and see what will be the result. So let's do the easiest example we could think of. An account charges compound interest of 1% per month. Calculate the equivalent annual rate. Okay, so it's easy. Your APR is equal to 1 plus, that's 0.1. That's 1.01 to the power of 12 minus 1. We said it's 1 plus r to the power of n minus 1. So it's 1.01 to the power of 12 minus 1. And the answer you will get is 0.1268, or as a percentage, it's 12.68%. Okay, so that means the actual annual rate, okay, the equivalent annual interest rate is 12.68% if you are paying a monthly rate of 1%. So when you go get your loan, you may be quoted 12% as the annual rate, and then they say, but you have to pay it monthly. That actually means the net that you're going to pay at the end of the year, because of compounding, is actually going to be 12.68%. Now that may seem like it's a small amount or a small percentage difference, but if you're investing in, if you're talking large amounts, imagine a person who is investing $1 million. That 0.68% counts for a lot of money. Okay, that's a lot of money. That's 6,800 actually. So that's a lot of money. It makes the difference. It makes a difference. So be careful when you're being quoted a rate to say if it's an annual rate that is being paid on a monthly basis, if they're giving you the equivalent annual interest rate or just the basic annual rate, because you may end up having to pay more. Now let's look at a little example. That's example number 3. It says £500 is invested in an account paying 1.25% interest per quarter. £500 in an account that is paying 1.25% interest per quarter. A, calculate the fund balance after 5 years. After 5 years. So here we're just going to use the formula S equals to X multiplied by 1 plus 0.0125, right? To the power of N, our N is 5. And then you get your value. Then B, find the annual percentage rate. The annual percentage rate. So the annual percentage rate has nothing to do with the amount that has been invested. So it's the same formula without the X, the principal amount. So you're just going to say 1 plus R to the power of N minus 1. Okay. Okay. So it says we're paying £500 quarterly. Okay. We're earning interest quarterly on that £500. It's quarterly. So to find the value after 5 years, the formula is still the same, 1 plus R to the power of N, okay? The principal amount is 500, like that. And then 1 plus 0.0, remember the percentage we're given is 1.25%, and it's quarterly. So it's 0.0125, and it's to the power of what? Remember, if we're paying it quarterly, that means we're paying it 4 times a year. And this is over 5 years. So how many periods are there? That's 5 by 4. It's actually 20 periods. So the actual sum will end up being £641.02. Like this. Okay? That's the value after 5 years. That's the value after 5 years. Now part B of the same question required us to calculate the annual rate, the equivalent annual rate. So it's the equivalent annual rate. The equivalent annual rate is going to be calculated as, remember we said it's 1 plus R to the power of N minus 1, which is 1.0125 to the power of N. How many periods are there in a year? Remember, 1 period is 1 quarter, according to this question. So how many quarters are there in a year? There's 4. So it's 1.0125 to the power of 4 minus 1. And the rate that you'll get is 0.0509. Like this, which is a percentage of 5.09%. That's the equivalent annual percentage. Okay, 5.09%. So remember, we used 4 here because there are 4 quarters in a year. We used 20 because in 5 years, there are 20 quarters. Okay, don't get it confused. Don't put 5 there because we're not paying annual, we're paying quarterly. So you put the number of quarters, the number of periods. That's your N. All right. So next we're going to talk about what we call sinking funds. Okay, a sinking fund is where you've got a fund in which you pay an equal sum every period. Whether that period is every month or every 6 months, it's every period you're paying the same amount of money in that fund. Okay, so for us to find the value or the amount in that account at the end of the period, we use this new formula which says S is equals to A in brackets, capital letter R to the power of N minus 1 divided by capital letter R minus 1, where R equals 1 plus the interest rate, i.e. 1 plus R, the small letter R. Okay, that's caps R, and then N is the number of periods. So A is the equal sum that you're going to invest. So it's S equals A multiplied by R to the power of N minus 1 over R minus 1, where R in this case is capital letter R representing 1 plus the interest rate as a decimal. So we're going to look at an example and do a little calculation to see how it actually works out. So the illustration says, suppose I pay £1,000 into an account for 3 years at an interest rate of 10% with all payments made at the end of the period, at the end of each year. How much will the fund accumulate to? Okay, so this is an example of a sinking fund where I'm paying an equivalent amount every year, and this amount is 1,000. So we said the formula comes to S is equals to A, then R to the power of N, right, minus 1, then divided by R minus 1, like that, like this. Okay, so what is my A? It's £1,000, And then R, we said R is 1 plus R, the small letter R, 1 plus the interest rate as a decimal. The interest rate is 10%, which is 0.1. So small letter R is going to be 1. So this R is 1.1. This is for how many years? For 3. So it's 1.1 to the power of 3 minus 1. All of this divided by 1.1 minus 1. Like this. So get nifty with your calculator. And the answer should come out to be 3,310. Like that. Okay, 3,310. Remember, I'm putting 1,000 every year. I'm putting 1,000 every year, and then I'm paid interest at the end of the year. So after 3 years, this is the amount, 3,310. That's what the account will be worth after 3 years. Okay, this is a very good example of a sinking fund. So looking at that past example, the question can be modified now to highlight when payments are being made at the beginning of the year. If payments are being made at the beginning of every year. So what that means is, rather than wait to get my first payment at the end of the first year, I'm getting my first interest payment at the beginning of the first year. Then at the beginning of year 2, I'm getting a payment. At the beginning of year 3, I'm getting another payment. You see now? So that means I'll get more payments by 1. Okay? I'll get extra payments by 1. 1 extra payment. So in that case, remember I was making 3,310. If payments were being made at the end of the year, I'll just add another payment, and that payment is going to be 1.1. Okay, an extra payment of 1.1. So it's that 3,310 multiplied by 1.1, like that. Okay. So if the payments are going to be occurring at the beginning of each year, the total sum that I'm going to get now is going to change to 3,641 pounds. All right, because I've got 1 extra payment. That is a receipt. I'm not paying more. I'm just going to get an extra payment my way. That's if the payments are being made at the beginning of each year. Okay, so be careful what the question is asking you for. Because if it's asking you for payments made at the beginning of the year, then you're going to get a different number of payments than if the payments were all going to be made at the end of the year. All right. So now we're looking at discounting. Discounting. This is the opposite of compounding. So far we've been looking at compounding, where we know how much money we're going to invest today and the interest rate we'll be earning on a compounding basis. And so we're asking ourselves, what would be the future value after so many years? Now, discounting is the other way around. We know the future value and we know the interest rates. Now we want to know the equivalent. Okay? We want to know how much is that worth today, in today's terms. So that's when we use what? Discounting. Okay? So it's a matter of simply rearranging the what? The equation. Remember, it said S is equals to, that's the formula for compounding was S equals to X multiplied by 1 plus R to the power of N. Now we want to find X, which is the present value. The present value, the value of a stream of payments or of a future payment today. So we simply rearrange the formula by dividing both sides by 1 plus R to the power of N. So the present value X is given equals to S divided by 1 plus R to the power of N. That's it. It's just a matter of rearranging the formula. Where S is the future sum now. S is the future sum, N is the number of periods, and then R is the cost of capital or the discount rate as a decimal. Okay. Now you see we don't call it the interest rate anymore. We're not calling it a discount rate because we're not compounding it. We're discounting it. So it's a discount rate. Okay. Now in net present value or IRR, when we get to our topic on investment appraisal, we'll be using the term cost of capital. We'll be using the term cost of capital, but it doesn't matter. You just know that they're referring to that R. Okay. So remember that formula. It's very simple. Present value X is equal to S divided by 1 plus R to the power of N. We're going to look at an illustration, a very easy one. So it says, find the present value of £25,000 receivable in 6 years' time if the interest rate is 10% per annum. Just that. Find the present value of £25,000 receivable in 6 years' time if the interest rate is 10% per annum. Calculate your answer to the nearest pound. The solution is very simple. It's equal to S, that's 25,000 divided by 1 plus R, that's 1 plus 0.06 rather. So it's, or rather the interest rate is 10%, so 1 plus R is 1.1. So it's 1.1 to the power of 6 for 6 years. And the answer is going to come out as 14,112. 14,112 pounds. So another way of looking at it is to say, if I know I'm going to earn 6% interest on an amount over 6 years, in simple terms, not compounded, in simple terms, how much do I need to invest today? Actually, it's compounded. How much do I need to invest today? If I know I'm going to earn 6% compound interest and I want to get 25,000 at the end of those 6 years, how much do I have to invest today? So by doing the calculation backwards like this, it tells you the present value or the amount that you must invest today for you to be able to earn 25,000 in 6 years. So that's 14,112. Okay. That's it on compounding. That's the basics of compounding. We're going to look at another example. Which is a bit more comprehensive, but once you get that, you have a fundamental grasp of compounding. We're going to look at another example. Which is a bit more comprehensive, but once you get that, you have a fundamental grasp of compounding. It says Charlie wins a cash prize in a competition. You must choose prize A, B, or C. The details are prize A, you receive 20,000 now. Prize B, you receive 27,000 in 3 years' time. And prize C, you receive £32,000 in 5 years' time. The bank interest rate is estimated to be 10% per annum for the foreseeable future. By finding the present value of each amount, establish which prize is worth the most to Charlie. So right now, just pause the video, look at that question, calculate the present value for all 3 prizes, then you choose the one with the highest present value. That's the idea behind it. So we're going to go through the calculations, all 3 of them together, and hopefully my answers that I'm going to get here will match with yours, okay? So we're going to start first by calculating the present value of that 20,000 received now. Now obviously it makes sense that the present value of £20,000 received today is £20,000 because it's already received now. But just to prove it mathematically, remember we said the formula x is equals to s divided by 1 plus r to the power of n. In that case, our s is 20,000 divided by the interest rate that we've been given is 10%. So it's 1.1, but n is 0 since we're at year 0, so it's to the power of 0. Now, if you remember your math correctly, any number to the power of 0 equals 1. So this becomes 20,000 divided by 1. All right, it becomes 20,000 divided by 1, which gives you 20,000. That's the present value. Now, of course, I know it's counterintuitive to try to prove that, but I just thought I had to put it in there so that you understand why the present value of an amount happening today or now is always the same amount. It's not going to change. So now we have the first one. The second option is winning 27,000, but in how many years' time? That is in 3 years' time. So for us to calculate the present value, we multiply, it's 1.1 to the power of 3. Okay. It's 1.1 to the power of 3. So it's 27,000 divided by 1.1 to the power of 3, and you're going to get 20,285. And it has been rounded off to the nearest pound. 20,285. And then the last option is to win £32,000. So again, it's being divided by 1.1 to the power of, but this is over 5 years now. Over 5 years. And this is going to give you 19,869 in today's terms. Okay, so which one should Charlie choose? The 20,000 or the 20,285 or the 19,869? So if we're just looking in terms of present values as the question has asked us to, then the best decision to make is this one. So Charlie should take prize B. Charlie should take price B because it maximizes the what? The present value. Okay. So that is the decision system if we're using present values. It has the most money in today's terms. Decision, or rather price B. Alright, so far we've been discounting using the formula x equals s over 1 plus r to the power of n. Now this can be rewritten as x is equals to s multiplied by 1 over 1 plus r to the power of n. Okay. Now this figure that we have here, this 1 divided by 1 plus r to the power of n, this is called the discount factor. Okay, it's called a discount factor. So there are tables that have been drawn up that have all the discount factors from 1% discount rate to 20% discount rate over a period of 15 years each. Okay, so you find these tables, they'll be given to you. You may find some of them in your textbooks. So please just avail yourself to them and get through them and understand how they work, okay? So the tables will have listed in them discount rates. For example, if you're asked for a discount factor of 10%, it's 2 years. You just go up the row to the first column, the first row in your table, look up where 10% is, then go down the column, match it to where there is 2 years, or n equals 2, then you take the figure that's there. That will be your discount factor for 10 years, 10% rather, for 2 years. 10% for 2 years, and then you get your figure. So this is the figure that you have in your table. So if you get a figure, for example, I know that the discount factor for 10% cost of capital or 10% discount rate, 1 year, the discount factor is 0.909. There are all to 3 decimal places in the tables, in the present value tables. So that means when you want to calculate the present value of something, of a cash flow, you just say S, which is the cash flow, multiplied by 0.909. Okay, it's that simple. Now you may find this formula 1 over 1 plus r to the power of n, written in another way, written as 1 plus r in brackets to the power of minus n. Don't let that freak you out. This is just mathematical notation. This little minus there simply tells you 1 over. Okay, so this minus sign just tells you it's 1 over 1 plus r to the power of n. So if you see it written this way, do not freak out. It's the same thing. All right, it is the very, very same thing. So now what we're going to do then is one little example where we have to use the tables rather than use the formula itself. We're going to use the tables. So it's just one quick example, and then we see if we can use tables on it. So let's carry on to look at this illustration then. Says, use the present value table to find the present value of £25,000 receivable in 6 years' time if the interest rate is 10% per annum. Now we know our S, okay, that is 25,000, that's the future value, that's receivable in 6 years' time. Now we need to find the discount factor. We need to find the discount factor, and we said we're going to use tables this time. We're going to use tables. So in case you don't have a table near you, I've attached a little table there on the previous slide, and you can use that one. Okay, you can use that one to try and see if you can identify what the discount factor is. So it's easy, just go look up 10%, then follow down that row until you get to where it says n equals 6, and you'll find that the discount factor is 0.564. 0.564. Okay, so if the discount factor is 0.564, then our present value is simply 25,000 times 0.564, and you get £14,100. That's the present value. Okay, now we did the same calculation before, but we were using the formula, and it gave us the answer of 14,112. The difference is because of rounding. That's because the tables are made to 3 decimal places, while the formula is not. So if the answer, if 1 divided by 1 plus r to the power of n, if the actual answer were at 6 decimal places, it has 3 other decimal places that have been cut off. So that's where the difference comes from. However, in the exam, they will ask you to use tables and tell you to round off your answer to whatever number of the decimal places, or to the nearest 1,000 or something. So you don't have to worry about that, okay? You can reliably use tables. So you see, tables make your work very easy. All you have to do is to look at the table. It's very easy to pick out what rate you must use or what discount factor you must use, and that's it.